Now, I want to be more specific about a problem. And this problem is actually, it's an eigenvalue problem. And it's going to come up in your homework. And let me write it down, and we'll walk it through. Okay, suppose I have the following. It still really becomes just a boundary value problem at the end. That's the important thing here. And here is something we've got to think about. Second order differential equation, this n of x can be, it's just a non-constant coefficient, it has this x-dependent value, right? There's a constant beta here, and I'm trying to solve for the psi of n's. And here is a boundary condition I have. So I want to do something a little bit sort of not so trivial, which is the condition here is that this function goes to 0 as x goes to plus or minus infinity. Now, first of all, you may say, well, wait a minute. If I'm going to solve this on a computer, infinity can't exist. Your computer does not like infinity. It doesn't like dividing by 0. It doesn't like infinity. Bad stuff. Okay? So, because if I were to actually do this, technically, if I were to go solve from negative infinity to infinity, it would take an infinite amount of time on a computer. Okay? Anybody got an infinite amount of time? Because then we can do it that way. But since you don't, and you have finite time, what we're going to already have to do is think about, what do you mean by this? I'm going to solve this thing. I want this thing going to 0 at plus or minus infinity. Plus or minus infinity don't exist. So really what I got to think about is, how do I reformulate that problem? Yeah.
X is a scalar or it's a vector? Does it matter?
X is a scalar. X goes from negative infinity to infinity. It played the role of t, what we had before. Psi, yeah.
Psi sub n. Is that a, what is that? Is that the iteration? Is that the iteration?
That's the function. That's the x-dependent function. It's going to have some shape. So I'm trying to figure out what this thing looks like in x. I'll talk about it in a minute. So it turns out it's going to be a bunch of solutions to this. So I put the sub n in there, sort of foreshadowing. Do you like that word? You don't use it in math class too often, but I like a big approach to education where you bring it all together. Okay. All right. And then also, you see that beta n in there? I know. You think, why did he put that in there? Whoa, he's foreshadowing even more things. I feel bad things happening. Not yet, but maybe you will. But anyway, you'll resolve it all in your homework. Like the conclusion, the plot all comes together beautifully. Okay? So the first thing is the following. By the way, this comes up in both quantum mechanics, electrodynamics as a standard boundary value problem. And part of this constraint here is just the fact that if this is an electric field, if this thing doesn't go to 0 to infinity, you have an infinite amount of energy in your system. Okay? Which is unphysical. Everything's constrained, bounded, so you have to do something like this. So the first thing we're going to talk about then is say, well, x goes to minus infinity to infinity. That is a mathematical idea. Infinity is a mathematical idea. When you go to your computer doesn't care about your mathematical ideas. All it does is add, subtract, multiply, divide. So you have to think about what it means for that. So potentially we could say, how about we do the following then? In a computational setting, what we really want to do is do this. Finite size domain. I'll make it negative L to L. Okay? Where I say, well, maybe L is big. We'll talk more about that later. What does big mean? Like a million? Sometimes a million isn't that big. Sometimes 1 is big. So we have to actually know something about the problem first. By the way, the one thing about computing is you should understand clearly that when you start setting up the problem, it's not like you just already know, here's all the value. You have to kind of know something about your problem first. The more you know about your problem, it's going to allow you to be successful in solving it. Right now, we have this thing where I don't know what L and minus L are. I know they're supposed to be infinity. Okay, well, we don't have enough information at this point to know what that means. Turns out for us, L is like infinity when it's like 1.5. That seems pretty harmless, right? So, but these are the kind of things you know after the fact, or as you start exploring your problem. There's more to this. What does this mean? It's going to 0. This is different than saying it is 0, okay? It's mostly 0, not 0. So this will play a very important role how we formulate this, okay? So understand, this condition does not mean the thing is 0. It's going to 0. Okay, so let's talk about that for a minute. And in fact, what I'm going to do is I'm going to even look at n of x here to be a very specific form. X. So it's like a little upside down parabola between when it's less than 1 and 0 otherwise. So n of x takes on some value, and so it looks something like this. The height of n0. This is what n of x is going to look like. So it's only going to play a role between -1 and 1. Okay, so we'll take that as our what n of x is. So now I can start addressing this question here. So let's look at the following. What happens as x goes to infinity? So first of all, what happens to our differential equation? What is n of x way out at infinity? 0. Oh, so then your differential equation becomes the following. Okay, if you're going to solve a second order differential equation, you should try to solve something like this. Constant coefficient, linear. Okay, these are about as easy as they get in terms of second order differential equations. And in fact, you can solve this. And you can write down a generic solution of the form. Now, the way you solve it, by the way, you always just put in a solution that looks like this, e to the lambda x. You throw that in there. That's how you solve differential equations. By the way, your differential equations background, right? So probably many of you took differential equations. You don't know how to solve very much with differential equations. I'm just going to tell you right now. I'm not saying just you, me, too. The only thing you really know how to solve if it's second order, linear and constant coefficient. Like the simplest things possible where you can put in things like this. Anything that's harder than that, you're done. Okay? But I just gave you one that was at that form. You put that in. And what you can write down is the following solution. Psi of n is equal to C1e to the C2. There. It looks something like this. You plug in, you find that lambda has to be plus or minus square root beta n. And there is our solution.